Okay, welcome back to Module 6. We're going to finish up the last half here. So this next half is getting into the point that you actually have your image. So Objective 6.5 is looking at contrast enhancement techniques to improve image interpretation. So as we mentioned before, that we've got energy that passes through the atmosphere, goes to the Earth, and then has to go back to the through the atmosphere to the sensor. So there are times that, especially if the sunlight isn't really strong, looking specifically at like early mornings, for example, then it's really hard to actually see the image. So what we need to do is apply contrast enhancement to see it. Other things too is that we can end up with a situation where we have or where there might be an error in the image, or that we've done some processing and it doesn't look quite right, or maybe we're trying to get one certain object to really stand out. Contrast enhancement will help us do that. So going back to talking about spectral signatures, which is kind of comes into play when we deal with the contrast enhancement. So spectral signatures are a measure of the reflectance of a particular range of energy. So if we have reflected energy and we have the original energy that comes from the sun or from the sensor itself, then we multiply it by 100, then we can get a percentage. So the reflected energy divided by original energy multiplied by 100 will give me my reflectance. Now, what spectral signatures are is a line graph that represents the reflection of each wavelength. So we come here, now we can see wavelengths. Now this is a very important picture here. This is something that we need to make sure that we understand and know and can decipher between. So because we have three major types of land information that is impacted and have very defined features. So for example, water is here, and water gets absorbed by the infrared spectrum, so that's why there's no reflectance. So it just totally gets absorbed in the infrared spectrum. And so we can see that water kind of goes up, and as it goes from the blue, it's high in the blue, it's really high in the green, and then it drops down as it goes through red, and then to the near infrared is gone. This is a very classic, clean, pure water signature. So here's my bands all on the bottom. There should be a thing on the bottom here that says our wavelengths. So we're looking at wavelengths. And so it's not necessarily a band, but we can imagine that we can separate it up. So 0.4 to 0.5 is blue, 0.5 to 0.6 is green, and 0.6 to 0.7 is red. Those are our bands. Then we have green vegetation. Now this is what is the big shock, right? So the green is, there's a good bump in green vegetation. So we can say, oh yeah, you know, it's high in the green part. But look at what happens in the near infrared. It is super high in the near infrared. So this shows me that if I'm going to look for green vegetation, I want to look at the near infrared spectrum because it's so high, and there's such a high contrast between water and soil because there's so much difference between them. Soil is kind of like a logarithmic curve in some way, a very low sloped logarithmic curve, and even though it has some dips here that are impacted by the the atmosphere, I should say, it for the most part is a pretty smooth curve. So with that, we can say, okay, well, you know, anything that's really high in the the mid infrared or the shortwave infrared would likely be soil, not vegetation. I was saying that what causes this green vegetation to be like that, I'm going to go back to that. Chlorophyll uses red energy to run photosynthesis. So that means that it's being absorbed. The red energy needs to be absorbed so that the plants can do photosynthesis. And that's what the chlorophyll does. Mesophyll reflects the near infrared, and mesophyll is the structure of the cell of the plant. So therefore, it reflects, if it's healthy, it reflects near infrared. So we can see how strong that is. So there's a good contrast between the two. And that's going to come up later when we get into transformations. That difference between the red and the near infrared is really important for us to look at health of vegetation and abundance of vegetation. So now thinking about how those are contrasting. So again, looking at this, we have lots of contrast, especially in the near infrared in this particular spectrum. We can start thinking about contrast. So I want to really make it clear as to what the difference is between enhancement versus transformation. So enhancement is like makeup. I can put on makeup, I can wash it off, and I look the same again. When I do a transformation, I actually physically change the image. So I can have a backup of the old one, but I create a new image entirely with a transformation. And it has new numbers that are associated with it and new properties that come with it. So it is like a physical change. It's like going in for plastic surgery. I can't really go back. So we take our images and we can either enhance them by making them look nicer on the screen, but not actually changing the true values of the image, versus transformations where we change the true values of the image to be able to enhance certain features or identify certain features in another way. So those are two terms that are very clearly defined in remote sensing. So I'm going to focus on contrast enhancement techniques today. So we're going to start with the first one, which is gray level thresholding. The idea behind this is that we want to have two numbers. We want to say this is this type of feature and this is not this type of feature. But in order to do that, we need something called a histogram. Now the histogram is a bar graph that shows the number of pixels on the y-axis and the digital number on the x-axis. So thinking back to what gray values I'm looking at. Now if we look at this histogram here, I'm drawing them with just like a wiggly line. That's because if I were to draw 256 bars, it would still look the same. It would just look like a big blob. So I'm just going to do that with these examples here, but just remember that it's actually a bar graph. It is not a line graph. So a gray level thresholding image, you have black and white. That's it. There should be no gray. As soon as there's gray, then it's not a thresholded image. There's another one that comes after this. So this only gives me black. So I set my threshold, and I say anything on this side is going to be black, anything on this side is going to be white. Generally, you would use it to define between two land features or specifically water and land. Because especially if you use the near infrared image and you put a threshold between the water and land features, then black would be water, white would be land. And it makes it very, very clear, and which also helps for identifying those small ponds that maybe you can't see visibly with just the gray values. So the second kind is known as level slicing. And so this one is when you put in multiple thresholds within your image. So you can have gray values in this one. So this is kind of like a little bit of a classifying in some way based on the histogram. So we look at the histogram here. I can place multiple thresholds and then I can set a value as to how it's going to display. So in this case, I would say, oh, I'm going to make these all 125, and so that they're going to be that level of gray. And then I can say the rest is white, that's above here, and anything below those two is going to be black. So that would give me 3 different features rather than just 2. Then we can get into contrast stretching techniques. And so these are techniques that allow us to improve contrast between pixels, and not so much for like dividing it up, but just improve the overall look of it, or try to enhance a certain part of it. So the contrast stretching is mathematically a little bit more challenging, but we're not going to go over the mathematics. So I'm going to just try to overemphasize what each of them are doing in terms of looking at graphs. So everything is done with a histogram, always with a histogram. So a linear stretch is when I'm trying to push my values, a little bit more values to the extremes. So I kind of draw a line between the 0 and the 255, and then I say I want a certain percentage of of blacks and whites. So I can say 1%, 2%, 5%. In ENVI, we have those options in there. We can tell it which ones we want. Optimal linear stretch is something that ENVI has as well, and you can use that. It just pre-calculates it based on the image that you're using. So And you can see here what happens to the histogram. So that I have more whites and more blacks, and then it's kind of flatter in the middle. Then we have the Gaussian stretch, and the Gaussian stretch takes everything and pushes it all to the center. So we have our histogram, whatever it looks like, and then it says, you know what, I don't want as many extremes, so I'm going to kind of make it a little bit more gray. And so it kind of pushes in the center and tries to make it look like a Gaussian curve or a normal curve or a bell curve, whatever word you want to use to be able to describe it. But that's what the purpose of it is. So it looks a little less contrasty and a little bit more homogeneous. Then there's equalization. So equalization is trying to distribute the same number of pixels to each digital number. So I could have it all over the place for my original, and then it just kind of makes them all about the same. So that's the equalization. You can always think of it as equalization is always going to be equal numbers across the histogram. Then we have contrast stretch techniques. So this is when we have our histogram, our original histogram of our image, and we want to increase the whites. So usually this is what we use for a very dark image. So we will use a logarithmic to kind of improve and increase the white values. And so that helps brighten it up a lot. So these previous ones, keeping in mind that the histogram, this original histogram, is always there in terms of number, but not as display. So you can think of this as this is the original image, and no matter what, if I go to a pixel and I look at the value of the pixel, whether I do this or this is just being the raw with no contrast enhancement attached to it. If I use this or this, I'm going to have the same value, which are like, how does that happen? Because this is an enhancement. It just makes it look better on the screen, but every pixel still maintains the value that it is. So that's why this is just like what does the screen look like? This is the original value or the original image. It maintains these numbers, but just looks differently. Okay, so difference between like the mathematical values that you would use versus the visual display of what it is. So then there's two more types of contrast enhancement, and these are done to a single grayscale image, usually done to thermal images. This is more common for that. So the first one is a color table, and actually I'm going to get you guys using color tables when we do transformations. So what it does is it applies a single color to every single digital number. So that means 256 different colors to a digital number. Now you can use gradients, so going from black to white that are all blue, or you can use or you can use multiple colors here. You can see how there's different colors. You can use different color schemes. You can reverse them if you like. But you can see how it's like more of a progress rather than just sharp changes, except for this one here. The 16 level is not really truly a color table. It is defined as a color table because it's preset, but these nice gradients are really nice for color tables and representing that data in a more understandable way. Because gray, we can only take 11 values from what we're looking at to the legend. That's all we can do. So if we can apply color, we can actually see about 16 million different colors. So it's easier for us to say, okay, that color relates to this part of a legend. The other one is a raster or color slice. It sometimes goes by raster slicing. The color contrast for this is, again, on a single image, like a single layer, and it groups all of the digital numbers into different classes and then applies a different color. So we look here, for example, you can see that there's two values in between each of these colors as we go, and this would be my histogram. And so what I'm trying to do is define, okay, between these two values and these two values, if it's this color, it's a pixel that's either 4 or 5. And if it's in this color, it's a pixel that's either a value of 6 or 7. And then it provides that color to that pixel. So again, we're just taking gray images and we're basically coloring them in based on that one value. So it's color by number. And we can group them. You can also make them with fewer values. So you start from here and go to here, for example, and make that 1, and then go from here to here, which would be 2, and then here to here to the end here would be 3. So we'd have 3 different colors, and I could go with blue, green, and red, and then that's all I'm going to see on my image is blue, green, and red. I'm not going to see any other color. So that's color slicing. Again, this is also done with thermal a lot rather than doing it with optical, but we can also use them for transformations if we're trying to highlight a certain area, like maybe an area that has high vegetation coverage, or perhaps there's an area where the soil seems to be diluted and wet. So we want to highlight that area and say that we need to investigate that. So that is contrast enhancement. So moving on to objective 6.7, it says to assemble the channels of an open source multispectral image in a remote sensing layered database. So these days it's actually really quite easy to do in ENVI. They've changed it so that it's super simple. You just need to open up your MTL file. So when you go to ENVI, you go to open, and then you find an mtl.txt file. So there's going to be a whole bunch of numbers before, and then it's going to say underscore mtl and .txt. That is what you're going to open, and they'll all open up, and it'll all open up stacked for you, which is fantastic. And it's going to be stacked, so you have your optical images, you'll have your panchromatic and your thermal all separated out into their own little databases. Now here, once we get to this point, you would resize this because you usually don't need the entire image. And because most of the pre-processing is being done like radiometric calibration, we can kind of go right to the size that we want. So you're going to type in resize, and you're going to find the region that you are most interested in. And I suggest using 2000 by 2000 pixels. And then you're going to move the little red box, because we're going to use the image version of it, over that area, and then you press OK. And then you can save that as resize stack as I have here. And then you can close the file that we had created or got from the MTL file, and now we've got this resized file. So now once you've got those open, you want to see everything in a composite. So the composite we talked about in class, where you're assigning red, green, and blue to different bands. So we don't need to do a radiometric calibration with Landsat 8. If you're doing Landsat 7, you'll likely have to do a radiometric calibration. But or anything older, you have to do one. So we can talk about that if you are in that situation that you're using an older image. But for Landsat 8, if we want to make a composite, we go to the data manager, and then you press the little arrow beside the bands word at the bottom, and you'll see red, green, and blue. Then you just click once the bands that you want, and just watch them fill in to make sure that the right one is going into the right color. And then you hit load data, and it will come up. So last but not least, you likely want to save a JPEG. So there is a chip to file, which means that there's a little, it will actually save the window that you were looking at as a JPEG. And generally speaking, that's a little bit better than the screenshots if you were going to give to a client. Making sure that you save the file as a JPEG when you do that, when you go to chip to file. You can use print screens in my class because I'm not super concerned about it being exactly a JPEG. But the nice thing about the JPEG is that you can save the JPEG file name as to what you've done with it. And then it allows you to remember, because otherwise with a print screen, and if you don't actually write notes below it in Word, then you won't remember what you did, or what numbers you used, or what composite you used, for example. So make sure you save it as a JPEG, and then you will be done. So in summary, for this particular module, we covered a lot of information. So the first things we covered was satellite platforms and sensors, and that was in the first video. And then in the second video here, we talked about contrast enhancement. And then I gave a little bit of an introduction just discussing ENVI, and you'll be able to either follow those step by step, or you can watch the ENVI videos that I have provided. So here's my references for the slideshow, and I look forward to seeing you in Module 7.